Maruf, am I audible?
Good afternoon, sir. Good afternoon. Audible, sir.
So today for this session, we have with us Mr. Ashish Shukla. He has also already delivered one session on first day. So I don't think there is a need for introduction. Ashish is today he is discussing a case study. So without any delay, I request Ashish if you can take over the session.
Okay, thank you so much for having me here again. And then thanks to all the participants for joining today. Give me 1 second. I think I need a power charger for my laptop before it dies. Sorry, I just missed to connect. Give me a sec. Huh?
Sure, sure.
Okay, are you still connected there? I'm audible.
Yes, sir. Audible, sir.
Okay, so let me share my screen. I hope you can see my screen. Just confirm so that I can start.
Yes, visible.
Okay, thank you so much again for having me here, and thanks to all the participants to joining the session. I know it's Saturday, it's after your lunch session, so it's now my task to keep you active during the session. And I'm back again here to tell you or explain you some more use cases. My purpose is to provide you the provide you the perspective what's happening in the power system, what are the challenges, and how the technology can solve those problems. You are expert in the technologies, but I can give you the perspective, and then so that you can think about that when you are engaging with the students, or if you're working on some projects, so that can help you to figure out in which area we should work so that we can solve the real world problem. So that's the whole objective. So my topic remains the same. Only thing is that I have added some more examples so that it can help you to the uh, build the new solution, build the new paper, write the new paper, creating the new solutions around that. So that's the whole objective. So I will start. So again, today I will recap because it was done a few days back. I think we had a session, I think 1 or 2 days back. So I just give you again quickly glimpse about that, what we talked there. And then I have added more examples too, so that you can relate how those technologies or how those problems can be solved. Same thing here. I just changed the picture so that you should not feel it's repeated. Otherwise, the power system remains the same from traditional to modern. Traditional, as you know, it's a bulk power production happening in one area. We have a huge transmission network. Then it comes to state buys from it extract power from the grid. And then and then when it comes to the state, there are different utilities, the discom distribution companies who provides power to your house typically. And then earlier it's all passive user, no one is generating any solar power and things like that. But what has changed now? So now you see we have EVs, we have now solar rooftops at our home, in factories, in industries. So then you can ask, what's the problem with that? So problem is that it's very difficult now, let's say first one, to manage the demand supply, because in the first use case, I can predict that how much is load could be, because based on the consumption pattern, date of the month, and then whether it's a festive season, how's the weather condition. So it's quite easy to predict my day-to-day demand for the power. But in the current scenario, when more and more electrical gadgets are being added, we have the EV, and then we cannot predict when person is going to charge his electrical vehicle. And EV is also a load, for the power system perspective. And solar, I cannot predict. It depends upon whether it's a sunny day or it's a cloudy day, and then how much production is going to happen, how much from the distribution company perspective, how much the demand is going to happen today. So it's very difficult to manage this demand supply thing. That is first part. Second thing is about the quality of the power, because like the solar or the wind farm, these are not the constant source of power compared to the traditional the fossil fuel based, where your generating station is running in the constant frequency. But in case of the renewable resources, it's not a constant. Solar generation depends upon the intensity of the light, whether it's a cloudy, not cloudy. Wind again depends upon the wind speed. So it's variable. The power which is coming into the system. So it's very difficult to manage the power quality. So these are the challenges. And also apart from that, we have the storage. Like the battery storage is also coming, because you also need the reliability of the power. Suppose if I'm running a data center, and then if I completely rely on the power grid or the grid power, then if suppose it goes, then how will I manage my data center? Because it cannot be off, right? It cannot be disconnected. So then we will keep adding the storage. Also some other use cases which I will be explaining with the battery. So these are the typically, in the power system perspective, these are the things which are happening, and it creates a challenge for the power engineers, or for us as a community, how to solve these challenges. This one I also explained. I can reiterate again. Just look at this curve, that what the net demand suppose if you're running a distribution company, how you see a net demand for the power. So like in the night time, there is no sun, load is also less, you see less demand of the power. When we wake up in the morning, sun comes, demand goes up. And in the daytime, in the middle of the day, when sun is shining, we get the ample amount of sun power, means the solar power, which is converted into electricity. Then in the evening time, again, the sun goes, sun sets, and then the generation goes down, and then in the night time we go to bed. Industry shut down, means not shut down, means industry stops working, and then you see the demand goes down. So what is happening in between? You see there are different layer. So why there are different layer? Because the net demand, which the grid or the utility will see, it is changing year by year. Why it's changing? Because we are adding more and more, the solar power into that. So this is a typical example of the California state in US. So you can see in the 2019, 20, 21, 22, in the middle of the day, the demand goes down, because more and more solar power is coming during in the middle of the daytime. So as I was telling you, that it's variable power. And then as a grid, they have to manage from very low demand up to the very high demand, which you see at around the 6 p.m. So grid has to manage, all these scenarios throughout the day. And this is about the smart home. I think I already explained, but again, give you the perspective. So as an individual, what is your aspiration? So as an individual, what is my aspiration? I want to switch to low carbon technologies. Okay. And then, so it means I'm caring for the sustainability. I want cost optimization, because that is also very important for me. And then I need the reliability of the power. And I don't want to compromise on my comfort and then, efficiency of my equipments. So what will I do? For the sustainability perspective, I will be having the solar power, right? So in the right picture, you see there are solar rooftops there. So I'm caring for the sustainability. I don't want to use the fossil fuel based energy. Rather than I want to generate my own solar power based electricity. And then I want to have the cost optimization. So what happens, as you see in the previous picture, in the middle of the day when sun is shining, I am having more and more, solar power. But if I sell to the grid, or if I have backfeed to the grid, I won't get so much, per unit charge, because overall the solar power generation is high during the daytime. So of course, at the cost when I'm buying from grid, buying power from the grid, I will not get the same amount of the money if I am backfeeding to the grid. So what should I do? I should store, this excess energy which I'm producing. How can I store? I can store in a different way. I can store, if I'm having the battery storage, I can store in the battery storage, or else just from the European country perspective, or the cold country perspective, where they need, they need the hot water for their domestic use purpose. They need, the space heating. For the space heating, also what they do, they use hot water circulation around their home so that their home gets warm. So what they can do when there is excess power, they can convert this electricity, the solar power electricity, to heat energy, right? They can boil the water, it is stored in the tank, and whenever it's required, they can use that. So these are the things, typically in the smart home perspective in India and around the world, it happens. Even if I'm having the EV, so in the middle of the day when I'm having ample amount of the solar power, I can use for charging my electric vehicle. So there is also, kind of, I would say, the use cases which you can see where the solution can be developed, where a person in a smart way should be able to handle everything. So if I'm having my app in my hand, and then I know how much is my solar power generation is happening, what is my connected load, should I buy from the grid, I should switch to, to my own battery storage and things like that. So this is as I was telling you, that I can give the perspective where, this innovation are happening, where this big companies are also working to develop solutions around that. So this is one of the use case which I am talking about. And I think last time I also talked about the energy communities. So in the previous example, we have seen as a home or as an individual, how I can contribute towards the sustainability, cost optimization, things like that. So the same thing can be done in the community level. How can it be done in the community level? Suppose, let's take the example of, if you are staying in an apartment, let's say you're staying not in the apartment, let's say you are staying in a row houses where we have the 20 row houses there, and some are having the solar power, some are not having the solar power, some are having solar power with the less capacity what they require. But as a unit, as a collective, community, we decide to exchange this excess power among each other. So what will happen? So in place of, if suppose in the middle of the day, if I'm having the excess solar generation, I should be able to share with my neighbor. Okay, so my neighbor, in place of now he's buying from the grid, he can utilize, or he can share my excess solar energy with him. So overall, we are optimizing our cost because together we are sharing. Okay, that's why you can see in the right hand side of the picture, it's the community layer where we are exchanging and then sharing the price. And then as I told you last time, that in some countries even they get benefit because they are not using the transmission network, so they get also cost benefit out of that because they don't have to pay to transmission network companies. So this is also one example. And then the challenges remain the same, because again it's a solar here, home is having the your electric vehicle energy, and then energy, home energy storage system and things like that. So lot of energy components are there. So now you have to integrate everything, you have to control in the real time, you have to manage the demand supply, you have to manage the power quality and things like that. So all these things, it creates a challenge. And I was telling you that utility level also, or sometime in the industries level also, people use battery storage. And this picture just depicts what is the application of this battery storage or the energy storage. So if you follow the line which is in a blue color, so suppose if this is my contractual agreement with the discom or distribution company, that this is the maximum power I will be withdrawing, and if I am withdrawing more than that, then of course I have to pay the penalty. So how can I save my penalty? So what can I do if I put the energy storage system? So when I am not using, or if my consumption level or my demand is below than the threshold level, which I have agreed with the utility, then I can use this power for charging the batteries. I can run my non-critical load during that time, and when my demand goes up, I should be able to do it reverse. So whatever the energy I have stored in the battery, I should be able to use in that way. So overall, I'm flattening my the demand so that I can save my money. So that's a use case which many utilities are applying, Discom are applying, even industries are also applying so that they can save their money as a form of penalty which they are paying to the utilities. And again, this depends upon how much they can save. It depends upon how much battery storage capacity they're adding in their premise or in their location. I will talk about more and more examples in the upcoming slide. So now, in a nutshell, now I have presented you all the scenarios, centralized to distribution, smart home application, energy communities. So overall, now I think you would have understood that challenges. So challenges that intermittency of the renewable sources, as I told you, that it's not the constant source of power. So there will be fluctuation, there will be power quality issues. Integrating this component into the grid, that's also creates a challenge, because suppose they have to also manage the power quality, everything, not only the voltage table, but also when they're injecting, they have to maintain the same frequency level so that it doesn't create harmonics to the system. Managing the demand supply, and then also the power storage. If they're having the excess power, how can I save so that it doesn't waste? uh, Cyber security threat, uh, because of the connectivity, and then now communication is everywhere, and then even the utilities, they are having all the systems in place. They have the SAP, they have the ERP, and then even the controls, even in the substations, they have connected to the network because of the data communication. And suppose someone gets control or someone able to hack the system, they can really damage the thing. So that is also very important, and that also creates a lot of challenge. So these are the overall, the evolving scenario, what is happening in the power system, and these are the key challenges which you see. Now coming to the technologies part. So this one I explained you also last time. I will again recap so that you remember it. Many things which I have listed, it's more than that, but I will take you some examples out of that. For example, smart grid. What is a smart grid? IoT and connected system, advanced energy storage. I will also talk about that. AIML learnings, use cases, and blockchain. So these are technologies which I also explained you last time, and I will just try to give you more context so that you should be able to relate it. So let's go. So now, we say in this word, data is oil. Why it is oil? Because earlier, when communication was a challenge, so it was very hard to send, the amount of data. But now, with the communication device are getting smart, so they are able to, share more and more, data points. So what is happening now? So earlier, what used to happen? So earlier we have the computation technology, so every device, protection, monitoring, or control devices, they are able to compute. They are able to take the local decisions around that, and then some level of connectivity. But as I said that now, with the communication, and then there is no problem, the storage and then computation. So now what is happening with more and more data, you are getting better understanding about the situation. And with more and more data, when you are having the better understanding, you are more prepared. So what is going to happen next? Okay. So what is going to happen next? It's also about, the predictability. So I am having the transparency because I'm having the more data points. I can predict because I'm having the more technologies like AI, ML. So based on the pattern, based on the generative AI, I should be able to predict what's going to happen next, and then I should be able to take control of that autonomously, and then finally adopt with the new situation. So that is the power of data, and then that's why it's becoming the reality, because now all the devices, whatever we use, they are smart, they are able to communicate. We have a lot of data available to get more and more insights. We have the good communication capabilities. We have the good, the cloud or on-prem infrastructure for the computation. So with that, we can develop more and more solutions. And then these solutions can help to optimize and then adopt automatically with less manual intervention. So that's the power of the data. So let's come back to the smart grid. So this picture is also very interesting. I thought to show you because we hear about the power grid. You would have heard sometimes about the microgrid, nanogrid. So just to give the perspective. So nanogrid is like my own home. Like earlier use case, I was telling you my home is a smart home. So it's like the nanogrid, self-sustainable. I am managing my own situation. Okay, microgrid is like the energy community, or within with industrial premises, where in my premises now I am managing my energy resources. I can have the battery storage, I can have my solar rooftops, I can have my own DG set generation and things like that. And power grid is like the typical that you understand. It's a bulk power transmission and things like that. So what is a smart grid? So basically what a smart grid does, it connects your microgrid to the power grid. So it it's allow to communicate between different systems. It allows how easily we can integrate various energy resources. It provides in the dynamic situation to take actions, control, and then monitor the things. So overall, this is what the smart grid is all about. So as we discussed so far, to have this smartness, what you need the real-time data, you need the communication, you need the automation, demand response, access power, storage, and things like that. So overall, then your system becomes a smart. IoT is also important, which I talked about last time. So this is one of the example. Like the power grid in India, they commissioned India's first fully digital substation in 2020 in Malarkotla in Punjab. You can read also in TND paper, a digital paper. So what they did actually, so they commissioned this fully digital substation. So several advantage out of that. So in the digital substation scenario, one first advantage, because it works on the process bus, means IC 1659-2. So the you would have seen in the big substation there is a huge bulky transformer, breakers, CTVT and things like that. So in place of having this copper wiring going from the switchyard to the control room, you can communicate via the optical cable. So basically you are saving the cost by reducing the copper wire. And then now it's a digital, means and then you can have more and more data points. And then as I told you that if you have the more and more data points, you can do for the diagnostic purpose, troubleshooting purpose, your assets monitoring purpose, you can do a lot of things around that. So that was the whole objective. So in the next slide I have just listed out some benefits, like for what purpose this digital substation can be used, like the reducing your transmission losses, voltage regulation, integrating the renewable energy, real-time monitoring and control, because you have the more and more data, you can communicate in a better way. And once you are communicating, you have the data, then of course you should be able to control as well. Predictive maintenance, I will also give you a very good example in the upcoming slide about the big transfer, how we can do the predictive maintenance using that. Compact design, as I told you, because it doesn't require copper now going from the switchyard to the control room. So, and then this also helps to to reduce the installation time, because now you don't have to lay out a lot of copper wire, but rather put two devices and then just put a optical fiber cable to connect between the switchyard to the control room. Fault detection, again, because you have the data and then it goes fast. Of course, you can do the rapid fault detection, you can isolate it fast. And then again, demand side management, again with the more and more data. Operational losses also, because you have the digital relays, and then there's also reduces the inaccuracy in the system. So these are the overall the benefit or the advantage which you can reap with the digital substation. So now I'm switching now to another topic. Now you have seen from the power system, digital substation, smart grid perspective. This is also but very interesting. I just wanted to give you a different flavor which you will not be seeing in your day-to-day scenario. So this is about the UK district heating use case. So what happens in the UK or any other cold countries where there is no dedicated district heating concept? So now you will ask, what is a district heating? So district heating means you boil the water centrally in one place, and then from there you distribute this hot water for the domestic hot water consumption or for the space heating purpose. So traditionally, what happens in the UK, all this, individual house or the apartment, they will have their own, heating, water heating, or space heating mechanism. And then for that, they need the fossil fuels. So either they will be running using the, the gas, or they can use electricity as well. So typically, this is how they use. It's in their house. So every house is having some kind of a heating mechanism at their home. If it is a society, so in the society level they will be having, and then they will be having this. You can see this red and then blue line going. So they are having this kind of a heating mechanism. But now UK is moving from from communal heating toward the district heating. So in the district heating, so in the centrally they will be generating or the creating or producing this hot water, and then they are circulating to the houses. So what will be the advantage? So in place of consuming this fossil fuels at every community or the house level, if you do it in the district level, then you are basically improving overall efficiency of the system. And I'm just showing you the picture on the right hand side, how this this pipe goes in the city, and then and then it goes from the city, and then it goes to different houses or premises. So this is happening, and then this as a UK 2050 vision, right now they have around 3% of district heating. So by 2050 they want to reach to 20% of the district heating. And in the right side of picture, you can also see how much carbon emission they are doing. You can see 17% contribution just coming from the space heating and then industrial heating. So you can see whatever the carbon content they are generating, or the carbon dioxide equivalent they are generating, 31% coming only from the heating. So that's why they are moving towards district heating to the communal heating to the district heating. And they also want to utilize all kind of energy resources, for example, ocean and sea, river, or any deep geothermal, whatever way they want to, if they are able to use that for the heating purpose. Very interesting. I have also heard about some of the data centers around the world. They also use this deep geothermal heat for the heating purpose. So what they do, they dig quite deep near the data center, and then this water goes down, and when it comes up, it's quite warm, and then that water they use for the the space heating or the heating purpose. Another thing what they are doing is like the large scale heat pumps. So in place of sending the hot water at 70 degree or 80 degree temperature, they can send it to some lower temperatures. Today traditionally they send this water around 80 to 90 degree centigrade temperature, and then user has to pay how much they have consumed. So how they will calculate? So basically based on the flow, and then how much temperature has dropped when the water exited from their house. So let's say I'm sending it 90 degree, and then if I'm using more and more, it means when it's coming out, it will be around, let's say 70 degrees. So it means 20 degree equivalent of, and then multiplication of the flow. They calculate the energy. So that much I have to pay to the utility or the provider. So now what they're trying to do, in place of heating it up to 90 degree, they can heat up to 60, 70, and then whatever is delta is required, which they have to compensate during the time, in the meanwhile, they can use some heat pumps. So heat pumps, what it does, it takes air, and then using the electricity, it makes it it brings its temperature up. So that is also the concept. So why I'm explaining you that these are the things which are changing, which are happening around the world, and in terms of energy efficiency improvement perspective, and then how we can reduce the fossil fuels usage. Now coming to the battery storage and other energy storage things, which I talked about previously. So you can see battery storage. This market this is also increasing quite a lot, because uh, in order to manage the invariability of power, and as I told you that though every countries they are adding more and more solar and then other non renewable resources, but how to store it when I'm not when it's not required, and if I'm producing more and more, then how to store it? Then of course you need to store in some other form. So battery is one form to store, and you can see the projection. So it will be adding more and more. So battery will be coming more and more in terms of install base in future. I just taking here an example, like in Germany, this is the largest battery energy storage system, capacity up to 35 megawatt hours. You can imagine it's quite huge capacity which they are adding. So this is happening. So utilities, discoms around the world, they are adding, the battery storage uh, to save surplus power which they are generating, to manage the invariability of renewable energy generation, so that they can compensate the invariability part of that. So this is one of the example. This one is very interesting. This hydrogen fuel cell. I think last time there was one question: what are the other ways to store the energy? I think you would have some session, but just to again repeat. So very simple to explain, but very difficult to now produce the hydrogen basically. Okay, uh, uh, it's not so much commercially available now, but this is going to be the future. So as I was telling you, very simple to explain how this works. So basically, what you need, let's say this middle picture is your battery. So you have anode and cathode. So and the one side you have to, through the compressor, you have to just introduce the hydrogen gas here, and then you have a electrolyte which will break this hydrogen to again ions, positive and negative. And then you have this membrane here, which allows only positive to go, and negative has to go through whatever the load connected in between, through in the electrical form towards the other side of the battery, toward the cathode side. Very simple to explain, but how to produce this hydrogen? And hydrogen anyway is so much in demand, not only for the electrical industry perspective, but also for like the farming, and then other industrial application perspective. So we don't have so much hydrogen generation as such, but how to produce more and more hydrogen. So basically that process is called the electrolysis process, where from water they break it down and then they create the hydrogen. So now you would have also heard about the green hydrogen. I also come across a very interesting thing. So it's not only about the green, it's a pink, it's yellow, it's a blue, it's a brown, and then it's a green, gray hydrogen. As I told you that to break it down, this water to hydrogen and an oxygen, this process called electrolysis, and then you need to provide the electricity to to happen. So if you're providing the green energy, renewable energy, then it's called a green hydrogen. And if you're providing using your nuclear power, then it's called a pink hydrogen. If you're using pure solar power of energy for this electrolysis process, that is called the yellow hydrogen. And if you're using some kind of underground energy, and then if you're using it and then doing this process, then it's called the blue hydrogen. Brown means if you're using through the fossil fuels, and gray is also like when you're doing with the methane and things like that. So there are different kind of hydrogen. Currently, today scenario, it's mostly used the methane one again, and then we use mostly the fossil fuel based electricity. But in future, if we are able to you get this hydrogen by using the water, and if we are able to generate do this electrolysis process using the renewable energy, then it will be pure, sustainable energy. So research, I think technology perspective concepts are there, but to make it, to scale it, to bring it to the commercial level, those things are activities are ongoing, and then to have more and more deployment in future, of course, it will happen, but of course there's some time by when this will happen, when we have more and more, the commercial installation in place. So yeah, so green energy, green hydrogen will be like when we are using the green hydrogen. So basically, we are not using fossil fuel, so we are reducing the reliance on the fossil fuel. This will be called carbon neutral because it's generated from the renewable energy source. We are not using any fossil fuel. We are not using any methane to create this. So, and then if it is commercial viable, then of course we will be having access to the low cost, renewable power. And then if we do in this way, the way it works are theoretically, then of course we will be utilizing low natural resources to produce that. So this is what, and then this one, it talks about, the projection, the forecast which I come across from the Bloomberg platform, that this is going to, explode in upcoming years. Now you can see it's very less in current scenario, but I think this is the more and more it will be, technology gets mature, commercial viable. I think we have the more and more, commissioned these things. I also just came across one example that, in US, that Bloom Energy is announced that they will have the world largest fuel cell installation in history, 80 megawatts, something like that they want to add. So this, which I come across. So slowly it will happen, but I think more investment is happening in the US area that I come across. In Indian companies also, they are investing a lot. The previous picture I was showing, it was from the Renew Energy, which is India-based, renewable energy company. They have invested in US, and one more company which I come across, that is the ECME. They are also in the solar energy domain in India. They also bought, I think, 300 plus acres of land in US, some part of the US, and then to establish and then to scale this up, this hydrogen generation. So this is going to happen, and this is going to be a big thing in future. Yeah, now AI/ML, another topic. This one I explained you that very simple term. I think I gave example of our vehicle which we drive, whether it's a two-wheeler or the four-wheeler. Like you have to go for the maintenance, time-based basically, or the usage-based. You can read 1, 2, 3, 4, 5, how you go up in your maintenance maturity model. So usage based means your car company says when you run 10,000 kilometers, come and then do the servicing. Time based, they say if you run for 6 months, then you have to come and then do the servicing. But of course, suppose if you get a choice rather than time based and usage based, if you do the maintenance based on the condition based. So if you know whether your vehicle is really required a maintenance or not, based on the conditions of your assets or condition of your vehicle, then you are going up in your maturity model. But to get the condition, of course, you have to have parameter monitoring so that you can decide whether oil is really deteriorated. You have to change your oil or not. So like that, that is like the condition based. Predictive based means now you have the condition known of your vehicle or of your assets if it is in the electrical network, and then now I know the condition. If I'm able to predict that how long I can run, okay, with that condition, then it's basically your predictive maintenance. So I know I'm driving my car more than 10,000 kilometers. Now I know the condition of my car, and then I know that the oil and the coolant are in the good condition. I can run more. And if I know the mechanism to predict, okay, you can run 2 more months or this much kilometer more, then I am going for the predictive based maintenance. Then if you go further up in this ladder, then you can go toward the reliability center or the financial optimizer. These are the different maturities there in the maintenance level. And more you go up, it means you are using the data. So right hand picture you see, basically in place of reactive, when you're going for preventive, condition based, predictive, then I'm utilizing the data, and then it's less human intervention. Okay, because now data is helping me to arrive to the decision. Okay, so I will take the example. This is very good one. So if you now imagine a very large power transformer installed into any utility or in the substation, 400 kV, 220 kV substation, it's a huge, large transformer, very expensive equipment, and then they have to do the maintenance. They have to change the oil. You would have seen sometime, big drums standing there. They have to, they have to change the whole oil into that, and then they cannot have, a lot of backups because it's very expensive equipment. You would have seen sometime if it is a single phase transformer. So suppose if it is single phase, 3 different transformers, then they have one extra. So that suppose they have to take it out one transformer for the maintenance, then they can switch to another transformer. So these are very expensive equipment. They cannot have more and more inventory or reserve equipments to as a backup plan. So what they can do? So if I'm having online sensors kept put inside, means are the connected to the transformer, it means I'm collecting the different parameter information. Voltage current, of course, I get using the CTVTs, but if I can get the oil information, and if I break it down, what is the moisture level into that, what is the dielectric strength remaining of the the oil, and things like that, then I should be able to predict better, and then I should be able to prioritize it better. When I say prioritize, means suppose I have a limited workforce to do the maintenance activity. So if one way is that, okay, every 6 months I do. Other approach is that I can prioritize. So I know, okay, my this asset is in the critical condition. It may break down. I have a mechanism. I'm using direct technology. I'm having the data. I know the condition. I can predict. So if I reach to that in the maturity level, then I can prioritize it better. So in place of doing transform A maintenance, I can divert my crew to transfer B, which is having the bad health in terms of performance. So that they can prioritize, they can do maintenance of that equipment. So basically, and this can be applied to any other, any power system, other equipment, whether it's a CT, current transformer, voltage transformer, breakers, transformer, you name the equipment, and then you have the connectivity. You put the sensors to collect the important parameter, and then we can do the predictive maintenance of that. Basically, you have to figure out what are the risks of failure. Okay, whether it's dielectric strength of insulation material is going down, oil dielectric strength is going down. Is there any hot spots which is building inside the transformer? What is the remaining life of the transformer, so that I can do the better, the planning, because it requires a capex planning. If I have to change, typically any big transformer stays 35, 36 years. But if I know how long it's going to run, and there are different mathematical models which are available. For example, I think for the transformer there's a IEEE model which you can use. So if you have your current voltage and then other parameter, you should be able to predict the life of the transformer. So the same way, as a community, like we are engineering community, we are academics, we are in the academics. So if you can develop good model to predict the remaining life using for this predictive maintenance practice, that will be really good thing. So because sensors are there, we are collecting the data, but how to use this data? So if we can develop the model which helps to prioritize, which helps to predict the life cycle, remaining life, and also if it can also suggest that, okay, if this is a problem, then what could be the probable solution? So if we can have such a solution or model available, then that will be really cool things. So as explained, if we have such a mechanism, use of technology into that. So basically, you reduce your failure event because you are monitoring, you are assessing the risk, you are informing that what is the trend, what is, and then when this may fail, and if we can notify, it's going to fail, and then proper actions can be taken. So with the technology, now we have now you would have, now you can imagine that a lot of technologies we have now talked about. So you need a good sensors, you need a good communication, you need good machine learning or the mathematical model, and then of course other things like other IT infrastructure. So if you have all this technology component in place, then this can be done, and overall you can improve the efficiency, you can improve, you can reduce the cost of operation and things like that. So these are the typical benefit if we are using AI/ML technology. So this is one of the example. We can have any other example, many more examples. I think this one I presented, you will get this slide deck anyway, so which you can explore. Like initially I was talking about the demand response. That is really a big problem. Every utilities around the world, they are facing. It's very difficult to manage because of various factors. As I told you, variability of your solar, your wind, EV connected, and the usage pattern. So this becomes a challenge, battery storage and things like that, because we don't know as a utility that when industry A or industry B, when they're going to use which source of power, how they're going to switch internally the things. So it's very difficult to manage. And if you can develop very good model, with AI and ML, that will be really interesting. So a lot of use cases. I just gave you the example of the maintenance, demand supply, any other thing. Many things can be done. Even one more thing which I come to my mind about the digital twin. If you are able to replicate your power system in a digital twin form, and then if I able to simulate different scenarios, that is will be really interesting. That is also reality. Many companies provide the solutions around that. So that is another technology piece which you can think of, like having a digital twin of the power system. That is also a very interesting thing. So blockchain is also interesting technology. I think last time I also gave you the example, but I will spend some more time so that you should be able to relate. So I think you might be knowing that this blockchain is like the distributed ledger technology, and its main advantage that no one can temper the data. You can rely on that. It's authentic source of information. So where we can use, so let's say if I want to apply blockchain in the power system perspective, so it means if I connect my energy meter and then the data goes to blockchain, so now you can rely, okay, this is consumption for Mr. A or Mr. B and Mr. C. And then energy community perspective, whether it was renewable energy when it was consumed or whatever source of. So if you have all this authentic data in place, then you can do many things. It can help in the trading perspective. It can help into monitoring perspective. I think last time I also talked about the net zero. So if someone has to authenticate, someone has to certify in that way. So I think this blockchain can help not only for peer-to-peer trading, but also for the monitoring and then tracking purposes. Yeah, so this was all from my side. And then if you have any questions, feel free to ask. Thank you so much for listening me.
So you can ask question by unmute yourself. Yes, Mr. Narayan Prasad.
Hello. Thank you, Ashish, for your nice lecture. And listening you after years is a good thing. Thank you.
Thank you so much. How to go to Zoom?
Anyone has any more question? You can unmute yourself and ask. It seems there is no question. So please give permission to me so that I can ask some queries. So Ashish, I just want to ask, your present employment, in addition to your means your previous employments also at ABB and Siemens. So this is a company which is known as the electrical related company, we say.
Yeah.
I wanted to know whether you employ only electrical engineering candidates or other branches also.
Other branches also. So as I have shown, in my last slide, so it's not only electrical engineering. You see a lot of communication, lot of computers and computer science things as well, data analytics and things like that. So we take people from all around other branches as well.
So why they people segregate the industries in somebody said that this is a core branch, some companies are called technology companies, some IT companies. Why this distinction between companies?
Okay, so only thing is that you can know, for example, if I come from the computer science, let's say I'm a computer science student, or if I'm the IT student, I know now the IT part, but I have to understand the context. So in what context I'm going to use this technology, right? So that's why they say it's a core energy domain, core industrial automation domain, and things like that, because then you are able to relate in that context. But it's not a showstopper, because what you study in the 4 years in your college, you hardly apply those learning, I would say. So anyway, you have to learn, acquire new things, and then so that your education, it's bit helpful, but that's not the only thing. You have to learn so many other things, I would say.
Okay. Uh, can you brief us on which type of projects you have worked on your career? What are design means? What a graduate student has to do in an industry from zero to the age of his maturity.
Okay, so I would say, okay, I'm still in the learning phase. So
But
okay, so
how a recently graduate student
okay,
evolves into a perfect engineer actually.
okay. So when we graduate, I would say we acquire the theoretical knowledge, I would say, but then it's about the application of my knowledge in the industry perspective. So what is important is that of course theoretical knowledge is important, and then the same thing which you are going to apply, but to understand the context, understand the domain. When we say, like, if I want to be expert into power domain, so I have to go into detail of the power domain, and then applying my learnings, my theoretical knowledge around that. So you start with one, then let's say I started, if I take my own example, I started, let's say, with ABB, where I started my career as a developer, hardcore, protection control and monitoring application algorithm development for 220 kV, 400 kV systems. So that is one piece which I started, core, hardcore algorithm development using the PSCAD, MATLAB simulation and things like that. But now I have to use it, now I implemented this. Now this has to go to a product. Now this has to deploy into a system. So now I have to understand other things as well, other component as well. Okay, this is my algorithm. It will be integrated into a device that is a protection device. Protection device will give a command to the breaker. Breaker is now a mechanical device. It's electromechanical device. So it has its own property, because when I give a command, it takes 40 milliseconds to respond and then open. There is a spring mechanism. There is, insulation, like the gas insulation system. When it happens, then it's a reignite. It's a reignition. Okay, that is a mechanical aspect. Okay, now my device is running there. Okay, how it will be, coordinate with the whole power system perspective. So there will be SCADA. So what is a SCADA? Okay, then okay, where this SCADA is there, then I come to know, okay, there is something called a load dispatch center. Okay, what is this load dispatch center? It's a regional load dispatch center. There's a national load dispatch center. Where it happens only in India, it's a universal concept around the world. So this is how you scale up yourself in the ladder. So you start always from the very small things, building your capability in one small area, but then this is how you scale yourself. You try to understand bigger and bigger things, bigger picture. So how my small contribution, it's making a big impact in the overall system. So this is how I would say for any any graduate, whatever you do good whenever you start, and then start understanding yourself, what is the big picture, what is the context, how my contribution is making difference into the whole big things and things like that. And then you start picking the different role. Like if I take my own example, I started as a hardcore development engineer, then I moved to program management, people management. I was IP officer. I went to the sales and marketing side, global business development. uh, I met several end customer around the world. I traveled, I think, more than 25-30 countries so far. Met several customers. So I played different role just to understand the big picture. Started my journey as a developer, then going to the different role. Now I am head of product portfolio management. So now my task is to define the future roadmap of our portfolio. So I work closely with the CXOs, managing directors, CEOs, to shape, where as a company we want to shape our portfolio. So in that way, you grow in the ladder, you expand your horizon, I would say, and then be passionate about whatever you do, and then feel proud about yourself with your contribution. So yeah, this is what I can advise.
Do you people need to go outside of your office?
Of course. So we have to go to outside the office. We have to travel. We have to meet in customer. So that's what I said, that I have traveled. I told you that more than 25-30 countries. I have traveled to US, Latin America. I lived in Europe for 4 years. I have been to Australia, New Zealand, and Southeast Asian countries in Singapore, Malaysia. A lot of countries I have traveled. So basically, you have to meet the end customer, how they are going to use product, what are the different practices which are used, because utility, this changes. As I was giving an example, what is the UK problem? UK problem is moving from your communal heating to district heating. Okay, so that is a problem space there. If you go to Sweden, Nordic part of the world, that is not a problem because everything is the district heating there. So what is problem there? Like the Germany, what is the problem for the Germany? They are 80 to 90% on the renewable. Okay, so the challenges, they are different because now they want to integrate all the renewable sources in variability and things like that. That's what I was giving an example. They're deploying 235 megawatt of the solar storage system. So that is a problem space there. If you come to India, what is the problem in India? So in India, discoms are in the bad shape financially, I would say. So now there is a government support for the AIMSP. You would have heard about that, deploying the smart meter so that you get the visibility, how much distribution transformer to the connected load means to the home we are giving the power, how much I am able to account that. So if you go to different countries, regions, you find a different problem space. Okay, and we are the global company, so we have to travel, we have to meet, we have to understand the local scenarios, and then develop our portfolio, develop our product accordingly.
Okay, so anyone has any more question? Participants? Okay, so thank you, Ashish, for sharing your valuable insights.
Thank you so much.
Your session was highly informative and engaging. So we appreciate the time and effort you took to prepare and deliver this presentation, of course, second time. So your contribution to our online FDP is invaluable. So thank you once again.
Thanks a lot for having me here. I know it's a very enlightened community. It was my pleasure to be part of this community and then presenting the session. Thank you so much.
Thank you. Thank you. So next session, we will start at 3:30. I request all participants to remain connected.
Okay, so I will drop off.
Yes, yes.
Okay, thank you so much. Have a nice weekend.
Bye.
Bye.
So next session will be at 3:30, but meeting will remain open. You do not need to leave. And I again remind you that assessment will start at 6:30 p.m. and before